Hello, everyone. Let's maybe start. So first of all, I'm really glad to see you all here in the room. I have to say that I haven't done a live talk on that big event since middle of 2019. So it's really great to be back, mostly because, of the pandemic. So that's a great feeling. I really love to see all the faces. So we're gonna talk about the code analysis. So I'm gonna touch a little bit of the philosophic part of it, about the code quality. We're gonna talk about code analysis specifically for C++ and its modern evolution and how it evolves together with the language, what it gets from it, what are the hopes, how the tooling is evolving. I'm not gonna focus on any specific tooling, so you'll see screenshots from various tooling. Definitely there will be JetBrains tools, but not only. So yeah, that's the plan for the talk for the next hour. So my name is Anastasia Kazakova. I work in JetBrains. Actually, I was doing C++ development in the embedded and networking area for 8 years. I launched 4G LTE networks, had all this fun. That was really cool. Then I moved to JetBrains, and I'm responsible for the product marketing, surprisingly, for all our C++ tools, mostly because I feel the passion for the tools and I love C++. So that's a good combination for the role. And you can usually reach out to me on Twitter, and the same name works for GitHub, or you can just, drop me an email at anastasia.kazakova@jetbrains.com. So I'm usually very helpful with our tools or any questions, so please welcome. So we're gonna talk about the code analysis, and when you talk about the code analysis, the first question is, why do we need it for? So why? And the obvious answer here is software quality. This is obvious, but let's try and dig a little bit into this philosophical aspect of what the software quality actually means. So stay with me for 5 to 10 minutes, maybe maximum. I promise not to get long for it, but it's kind of important so that we are all on the same page. So if you ask yourself about the software quality, try to think about maybe 1 or 2 or maximum 3 words that describes the software quality for you. So just think in your head, okay? I asked that question on Twitter many times. I asked my colleagues, I asked people around, and I got a huge list of answers. Some of them I hear, those which I usually hear quite often. So there are different words. So like the people say that it should be like readability and maintainability, which is kind of close and related. Testing, like security, reliability, good API. Less undefined behavior, probably coming from the C++ audience, you might guess. Documented, like expressive code, whatever, like reviews and testing are also there. Size, which means the reasonable size for the tasks you are solving with the code. So there are many words, but surprisingly, there is a specific consortium which made a formal definition of the software quality. And they actually selected these 5 words: maintainability, security, reliability, size, and efficiency in terms of the resources. I don't know, that's their choice. I would probably select a little bit different set, but that also works for me. So the idea is that you need to decide what you mean actually when you say in software quality, what is more important. I guess for different maybe areas and tasks and focus, the definition might be a little bit different. I mean, like real-time systems, the networking I was working at, or the automotive, they might have slightly different focus than other systems. That's fine. But at least we understand that there are these things which are important. And when talking about the software quality, I have to say that I really like the article by Martin Fowler. I know we're JetBrains are keen with Martin Fowler because of his refactoring articles, but he has a very good article about the trade-off between internal and external quality, and the idea that there is actually no trade-off because both are important, and the internal quality guarantees the external quality, and this is the graph how they evolve. So you probably understand the idea. So if you design the system badly, there will be no external quality in a while. So it might start from the beginning, but while you're working on the system, you're extending it, everything just goes worse, and the low internal quality actually affects how it looks externally. Okay, so the software quality is something we usually care a lot. So there are lots of articles, there are lots of these words which kind of important for us, and we want to make our quality good enough in terms of the the software quality. And if we, as a C++ developers, if we think what we also have in our head when we think about the software quality is lowering the frustration. Because the bad code is actually very frustrating, you know. So when you look at the bad code, especially when you you open some code base and you see like, oh, what's going on here? What a bad code. You're really, really frustrated. You don't want to spend your time on, you know, improving all that stuff. And there are lots of specific C++ related frustration, which I would like to highlight here. I took a look at the C++ Foundation C++ Developer Survey Lite results for this year. Surprisingly, for this point, they're nearly the same as like previous 2 years. So I was actually opening this year results to update my slides, but I haven't updated any single number nearly. So these are the frustration points for C++ developers in 2022. Let's take a look. So yeah, so it's kind of, the colors are a little bit different from the original, but actually here are 3 colors. So the parallelism support should be in like kind of pink one, because that's for the language. So that's the point, like that the developers are missing some language support, some library support for the parallelism. The other colors, the yellow and the blue. So the yellow is something which is coming from the language. The blue is something which is coming from the tools, like from the ecosystem. You can see that the blue actually dominates on the top. And yeah, that's the ecosystem we live in. So for many, many years, we have issues with the ecosystem in terms of the tooling, in terms of the package manager, build system, whatever I can say here. I think, it has something for you in terms of the frustration points from the C++. But the yellow part is language, and I'm actually gonna focus today on how to catch up with this yellow part. So how to limit these frustration points for the yellow part. So for the blue part, kind of maybe unusual to hear from the person from the tool vendor, but I'm not gonna deal with it right now. C++ frustration. So where is it coming from? Let's look at the example. I like it very much. I show it very often in my talks. And this is an artificial example. It came out of our QA engineers who created a case for testing some feature in the IDE. It doesn't matter which one. It doesn't matter what they were actually doing. The thing was that this is a example in C++ which you can compile successfully. And it broke some feature in the IDE. And the question from the developers was actually, what this code is actually doing, why does it look like that? And you know, after some discussions and some iterations, we found out that that's the code. That's the same code. That's all that it does. It actually just returns this answer to life universe and everything, and that's it. So if you remove all these templates, variable templates, all this cast, you just get return 42. And that's absolutely correct code, just the same as the one on the left. And that's probably one of the issues pointed by many people nowadays. At least I captured a few quotes from Twitter, surprisingly mostly coming from the game dev guys. I don't know why. Probably they see that more often, or they're more frustrated than others, or they're just more loud than others. So yeah, Tim Sweeney from Epic Games, Aros working in Unity. The point here is that we literally have 10 or 100 ways of doing one simple thing in C++. And that happens to us. So we have many ways. We have a very powerful language. We make it even more powerful every release. And sometimes we found out that, we can do one thing in many ways. Like in this example, when we have this return 42, and I can write it in, for example, this way. So this is the frustration coming from the community. And the reason is that if you have 10 ways to do one thing, there will be people, even in your team, who will be using all the 10 ways to do that. And like, if you read this nice book by Google engineers about software engineering Google, that quote was about the API. With the sufficient numbers of users of an API, it doesn't matter what you promise in the contract, all observable behaviors of your system will be dependent on by somebody. The same applies to the language. If you have 10 ways of doing a thing, they will be used. And quite often, at least half of them will be used in your code base. And you have to kind of spot that they're the same and kind of, you know, apply some guideline probably to make them look similar. And this is a very important point of frustration. I actually hear it now even more often, probably because the language gets, it tries to be simpler, but it also gets more complex because it becomes more powerful. Like, because we're getting more approaches to how to do things available in the language. Another thing which bothers C++ developers a lot, and you probably see that in the list of my keywords defining the software equality, is the limiting the undefined behavior. The undefined behavior is not good, we know that. And there is a very nice story about the Linux kernel and about the vulnerability, which luckily wasn't like that dangerous, so it was captured by the developers early, so they fixed that quite early, but they, after that, and big thanks to them, they actually wrote a nice article about that. I will publish the slides, there is a link, so you can find the story about this vulnerability in the kernel, and just look at the piece of code and find the line where the issue is. It is here. We're referencing the pointer. We're not checking anything. And the funny thing is that a little bit later, just a couple of lines later, we're actually checking this pointer. But because, you know, GCC optimizes this check, because you already referenced the pointer, there is no reason to check something which was already referenced for the compiler. It just optimizes it out. So, there is a huge article explaining how to get some, you know, dangerous code and execute it in the kernel. So you can like read through it. So yeah, and this line was like, it was occasionally added. So there was some mistake why this line actually appeared in that place. So there's a full story in the article. But the reason is that, yeah, undefined behavior could do some, you know, dangerous stuff to us. And we know that. And that's why we don't like it. And yeah, even when we try to protect ourselves, compilers, which are smart enough, sometimes help in the, you know, opposite direction. They doesn't help actually. They can optimize probably a good check here. Okay, so why do we need code analysis? So we need it generally to improve the software quality. We want to decrease the developer frustration because no one likes to be frustrated about the code. And yeah, specifically for C++, we would like to catch and to fix some C++ pain points, especially like, you know, undefined behavior, which we all don't like. Okay, one could tell me that, okay, I just don't need the whole code analysis stuff. I just use 3 V's. So VOL, V extra, V error, and I'm safe. But, you know, the problem with it is that, like, there is a big story that compiler can't catch everything. There is a story that you probably don't want these 3 V's on your code. But the practical side of the story is that even to use that, even if you want to have this VOL, V extra, V error, you need to find out the way how to do that properly. And because you remember this blue part of the frustration points with the build systems. So what is written here is the upper part of the slide is how you do that in CMake. The lower part of the slide is how you do that in make files. That's first. So you need to understand which build system you are using to pass this flex properly. Then if you're on with MSVC, you have this V4 and VX, or you have this VOL, V extra, V error, which is luckily the same for GCC and Clang. If you use some custom compiler, maybe you have other options here as well. So So, okay, you need to find out which build system you're using, which compiler you're using, which flags it support, and to pass them properly. And the trick about the make files, because like I was working in embedded, I was dealing with make files for 3 or 4+ years. That's the creepy project model, actually, to be honest. And I did that mistake when I was, I would say, yeah, beginner. So I passed these flags not via the 6 flags, but CPP flags. And CPP flags is a flag for preprocessor, not for the compiler. So don't do that. Anyway, the idea of the slide is that even to pass the simple, to turn on all the compiler warnings and turn them into errors, you need to know how to do that properly in the ecosystem when we don't have the standard compiler and the standard project model. And that could be a challenging task. And yeah, talking more about the challenging task, this is the distribution from some statistical research, 2 of them done by JetBrains. This is the developer ecosystem research in 2020 and 2021. I still don't have data for 2022. It will be available in a couple of months. And the foundation for 2021 research. Anyway, you see we have lots of project models we do use. CMake is kind of growing. That's what we know. It's still not the standard build system, but used by many. Makefiles are still very, very popular, especially in some, embedded between embedded developers. Amazbuild, Microsoft thing, but also very, very popular for game dev, obviously. So they use it a lot. So they rely on Microsoft's project model a lot, like Xcode and all that stuff. There are many things. There are also like Bazel here, Mason here. There are many, many things we're still using. So if you have a task of passing the compiler flag, first of all, you need to think how to do that properly in your specific ecosystem. Okay, but maybe we can do better. Let's see if C++ itself can do better, if it could actually help us. That's the language we're using, and when you're using something, the language is also a tool. When you use something like a tool, you want it to be helpful. You want it to help you. So if you're using C++, you want it to help you. To preserve the better quality. So there will be just a few examples of how C++ is actually doing better these days. This one I really like because I came from the area when I was logging and tracing things quite often, and I was always doing that with macros. You can't avoid them, even though I'm very skeptical about macros, but you can't avoid them in many areas still. But we are trying. I mean, as a community, we're trying to make an attempt to somehow avoid them, or at least to limit their presence. And I think that state source location from C++20 was a very good opportunity for us to avoid at least some parts of our macros, some shares of it. So macro style logging and tracing could be avoided if we use state source location. And yeah, so for example, here we have on the screenshot, there is actually a check by the SwannerLean tool, which actually captures the situation that we have a tracing function and we're using macros, and we better use state source location, and it can even help you, and you can transform the code in the way that you use state source location. So it might look longer, but believe me, in a couple of iterations you'll get used to that, and you'll love that much more than the macros. But there are still a lot of macros in the ecosystem, but yeah, so we can at least try in some specific direction. Contracts. So I don't have a big slide for contracts, and that's unfortunate. That's because we still don't have them. I have a few proposals linked here from the recent discussions, and I'm really looking forward to them from the perspective of the code analysis, because they give a huge opportunity for every code analysis tool to help us, because there are all these pre-and-post conditions. There are things which we could check. There are things which contracts could help us check. So because this is a way for the developers to set their expectations from the code, and then the tool could help checking it. But yeah, unfortunately for this slide, nothing more than just links to the proposals. I'm still waiting for us to have them. A little bit more about the lifetime safety, because this is what bothers C++ developers for a very long while. This is the thing we look at when we, for example, talk about Rust. This is the things we feel a little bit envy about. And there was this attempt from Herb Sutter to introduce this proposal about the lifetime safety. And yeah, it actually helps capture the things like in this example with the dangling iterator, and it actually happens to dangle because, yeah, I have a pushback here. So, and if the relock happens, then I have a dangling iterator. So it would be good if I can, you know, catch that. And actually nowadays, there are a few tools which help us support that. So I have the proposal like suggest us to do that. There is this concept of owner and the pointer. There is this suggestion about the building compiler checks. There was even like, yeah, some implementations via the GSL library annotations. Practically, what we have is the LVM branch. They state, like the authors state, that the overhead is quite small, like 5%. You can try it -v lifetime. It doesn't have many checks, but at least something, so you can, like, you know, see how it works. There are also, of course, the C++ core check lifetime rules in Visual Studio, and we also implemented some of them in C-Line. So there are tools now which can help. Like, unfortunately, I don't think for now there is more going on for the lifetime safety than this, but like, let's see how it goes further. So at least we have some, you know, we have some proof of concept that we can do that in C++. So maybe we're far from Rust, but at least we can do something. So that's not the problem which is completely unsolvable, because sometimes the people say like, okay, you want the lifetime, just go to Rust. Stop. We can maybe try in C++. And it's good to see that we're doing these attempts. I mentioned that in C-Line we were implementing the lifetime checks via the data flow analysis, and I would like to talk a little bit more in details about the data flow analysis, because to my extent that's the thing. That's what could help us catch many errors, and it's practically, so we did that. We implemented data flow analysis in C-Line. We know that it's possible. So we can have more tools supporting the data flow analysis, and it's very powerful. So what it does, so if you don't know, so this is the analysis which takes into account like function parameters and arguments, function return values, fields, and global variables, and it tries to output some value ranges for the variables in your code and make some guesses based on these value ranges. So what could it actually guess? For example, if you have some, you know, local piece of code, for example, inside the function body, so the local data flow analysis can easily capture the dangling pointer. So that's easy. So in the situations like that, yeah, it can see that you are deleting the pointer. So yeah, you probably have a pointer to a deallocated memory. Moreover, you can do that in the global scope. That's also possible. So you can write a global data flow analysis. It works in the scope of the translation unit. You can do the same. So even if you are deleting the pointer in some other functions, and that's what we usually do. So we're not, you know, if we're deleting the pointer inside this the for loop, that's probably just a silly piece of code. But quite often, yeah, it's hidden somewhere inside another function in the same translation unit. And data flow analysis could actually capture that, and it could say that, yeah, you still might have a pointer to a deallocated memory because, like, yeah, in that function you were deleting the pointer. Apart from dangling pointers, data flow analysis could actually capture many other things. So, like constant conditions, like it could guess through the value ranges and said that this condition is always true or this condition is always false, or it could say that this is the dead code, like unreachable code, or endless loops, which, like, endless loops are good sometimes, especially if you work, you know, in the you write the code for the microcontrollers, you often have the often loops. That's okay, but you need to understand that you're doing that on purpose. Sometimes endless loop could be a mistake. Infinite recursions, the same, like unused values, dereferencing null, dangling pointers, and yeah, index out of bounds is also possible with the data flow analysis. I want to show a few examples of how it works, and as I said, we did that, we implemented that, we know that that's possible, and that's the analysis which doesn't decrease significantly the, like for example, we did that in the IDE, we're measuring the performance, we know that it doesn't decrease, you know, your, doesn't affect your typing or how you work with the code in a significant manner. So, unreachable code, this is the example, so I have this function consume, I'm calling it with the value processing and idle, so the code with the case stop is unreachable, and that's what the data flow analysis could capture and show me here. That's just an easy example. You can guess that example could be much more complicated, and data flow analysis could also capture it. You just need to set a proper, you know, limits. Sometimes data flow analysis could be long, but you need to set the limit that if it's working too long, let's stop. So it's not a silver bullet, but it could capture a lot of cases actually. Index out of bounds, I think we tried recently with the data flow analysis and succeeded, so that you could actually analyze this and see if you're going out of the bounds of the array, or that could also work with, you know, with the strings. So that easy. Again, the example is quite simplified, but you get the idea. So it could be a little bit more complicated, and data flow analysis will still capture it. And this is quite a useful check. I have to say that when we implementing the new checks, we're usually running them on our code base, and there was never a situation when we haven't captured anything. So that means that's a good check. I mean, so yeah, talking about the practical implementation. So as I said, we did that. We know that that's possible. So we implemented data flow analysis a long time ago. We moved it to Clang. We made it global for translation units, and we keep implementing new stuff on top of the data flow analysis, like the index out of bounds was our recent experiment, which worked well, and there are more things we're trying to create. The obvious question here would be, can I do more? Like, because I was talking about the data flow analysis in the context, in the scope of the translation unit. Actually, this is possible. You can do cross-translation unit analysis. There is some approaches how to do that described in the LVM documentation. And there is even proof of concept, I would call it, like CodeChecker from Ericsson. They demoed it at some LVM meeting several years ago, so the code is still on GitHub. You still could play with it. It works using it could work. There are two approaches. It has two passes, so it's either doing the pre-damped, pre-compiled headers, or it generates AST on demand. It depends on what you are trying to save more memory or CPU. So, but it works. It's quite heavy in this proof of concept repository. It can do some very, very simple stuff. I mean, like the set of checks, there is really just the proof of concept. So there are no really complex checks implemented in the repository, but it just proves that this is possible. So we can kind of improve it more. And I hope that that would be the next step for the code analysis, for the data flow analysis for C++, that we can actually make the cross-translation unit analysis and make it for the whole program. Okay, data flow analysis, that was it. Now I can't talk about the code analysis in more than C++ without talking about C++ core guidelines. That's a very popular topic. I'm not going to explain you everything about the core guidelines. Better get the Kate's and Guy's book and read the beautiful C++. I have this book. It's awesome. I really recommend you reading it. I would maybe like to discuss the core guidelines from the perspective of the people who are creating the tools and how we look at the guidelines. Because every time we look at the guidelines, the first thing which we ask ourselves is if they're toolable, and if it makes sense to make them toolable, if that makes sense to push them in an automatic way and throw them into developer's face, because sometimes you don't need that. And that's what I'm trying to explain here. That's what I'll be trying to do now. So first of all, there is a big part of the core guidelines checks which are easily toolable. So they're even written in the way that you can, just code them. So this is just the quote from the core guidelines. I maybe swapped a few words just to highlight that it's easily toolable, because that's just, nearly the piece of code. This is just the example. Rule F16, so for in parameters, pass cheaply copied types by values and others by reference to const. There are rules how to detect the issue, and that there is the rule what to do next. So you just implement that and yeah, you are done. You have a check. That's awesome. It's automated. You don't need to think about it anymore. There is also a group of checks which I called abstract. If you were at the Kate's abstraction keynotes today, that's about it. So there are things which are about the abstractions, which are about the things which is not that easily toolable, and I'm even not sure that it has to be toolable, because that's the abstraction, and abstraction is something you create and you analyze in your head. That's the machine can't easily do that. There are some aspects which can be automated, but not all of them. For example, there is this rule that you can detect identical and similar lambdas used in different places. I don't know if you ever search for searching duplicates in C++ code. There are tools which can do that. They can even work in reasonable time. They can search duplicates even if you have renamed the variables and maybe swap a few lines of code. They will find the duplicates, but they're not ideal. They're just even if you copy paste some piece of code, they will find it. But if that's just the code written in another way, they won't be able to do that. And remember the example about returning 42. If we're talking about searching for duplicates, we have to understand that the code might be written in different ways, and that's still the same code. And I don't think that there will be tools which could easily detect with the 100% guarantees that this is a duplicate, given this fact, while we have that. In that sense, yeah, I think that these rules are kind of the rules which we still have to apply. They are good rules, but the tooling can help you with them a lot. It can maybe highlight some things that this looks maybe similar in some simple cases. Or it can say that if you set some heuristics, and that's you who is setting these heuristics. Because, when I was studying the university, I had from some old professors, I heard that yeah, you can't do the functions more than one screen long. Have they seen how we use the screen nowadays? Usually they're turned 90 degrees. I don't think I want to see the function sometimes that long. So it depends. This is the heuristic. This is the number, so you have to configure it. So if you have a way to configure this heuristic, sometimes the tools could help you, but they can't fully automate the applicability of this rule. So that's still the input from you which is needed here. Yeah, and that's what I talk here about is this example, because if you're searching for duplicates, yeah, again, this is what could maybe break the rule for you. There is also a third group of guidelines which affects interfaces. So these are these rules, for example, F4, if a function might have to be evaluated at compile time, declare it const expr. Then there is rule F5, when to declare inline, and F6, when to declare no except. This might be a good advice, but when you're doing that, you have to understand that you might be changing the interface. And then there might be some reasons for you to have this interface, and that there might be reasons why you have it that way. So from our perspective, and we had lots of argues about that inside the team, if we have to push these kind of rules on the developers, because if the rules affect the interfaces, not all the developers would like to see their tooling pushing these kind of rules on them. So in that sense, we decided that no, so probably we won't be touching the rules which affect the interfaces a lot. We might suggest some kind of intention when you press something and it suggests how it can transform the code, but it's not something which is highlighted as an error in the code. Okay, so talking about the tools, actually, I think core guidelines, they have a pretty wide range of tools which kind of support them right now. So there is this guideline support library, there is the Visual Studio Core guideline checkers, Clang Tidy has quite a bunch of checks from C++ core guidelines supported. Sonar tools like in our tools like C-Line and V# C++ as well, but no single tool to check them all. And probably there are reasons for that. So probably that will be the case. So yeah, that's about the core guidelines. Let's move forward. And talking about the analyzers, actually, there are analyzers for general C++, for just the code any of us write. But there are also quite nice DSL analyzers, so analyzers for some specific domain areas, which we quite often using, and I think that's correct. So like there are MISRA and AUTOSAR specification for like various embedded stuff, automotive stuff. There is Clayzy analyzer for Qt. There is like, for example, Unreal Header tool analyzer for Unreal Engine code, and much more. So quite often, if there is the big area, there is some domain, there might be some specific domain analyzer for that, in addition to, you know, general C++ analyzers. So because it knows more about the domain, so it can analyze the things beyond the general C++ stuff, and it can help. And I would like to talk here about just one of these cases, and that's MISRA, like MISRA and AUTOSAR, and about how it evolves in our mind through these years. Because when I was working in the embedded area, MISRA was mostly like go and certify, just pass the checks, get the certificate done, or like fail. But now I see more and more developers who do request the MISRA during the development stage. I mean, like they want it while they're developing the code, not when they are going, you know, to someone to certify their code. And that's quite understandable for me. And I'm like even surprised that it happens only just maybe, I don't know, 5 or 6 years ago, when I started noticing this trend a lot, that there are many developers who need MISRA and AUTOSAR who request the tooling to support it. Because when you have these checks at the development stage and not at the stage of certification, like, you know, the cost of the error, because if you have to fix something, you'd better fix it right away when you're writing the code. That's obvious. Also, like, you can vary the set of checks you're, you know, running when you're at development stage, because when you have the certification, you just need to pass some checks which you're obliged to pass. And it's strict. You can't, you know, change it. But maybe you want to do it in several steps. Maybe you would like to first of all, you know, eliminate one group of checks while you're just developing the code, then focus on something less important, and so on and so forth. So you can customize the list of checks you're, you know, using. And quite often, if you have a tool like which is helping you on your development stage, quite often it suggests some quick fixes, which is also good, because you can fix the code immediately while you're developing it. And that's probably why the trend to get like MISRA on the development stage becomes more and more popular. And I see the tools supporting MISRA more and more. The code analyzers, the IDEs, they are bringing MISRA to the developers, right to their like tooling when they're developing the code. Some statistics I got from the tools I know which do support like MISRA, like the general tooling. We started supporting MISRA in C-Line maybe a couple of years ago. Sonar tools like have these like MISRA checks. PVS Studio I know has some, but I actually failed to find the statistics which exactly checks they do support. They don't have it properly in the documentation. So I don't know. But it's good to see that these numbers actually, this slide I was updating a lot last night, because the numbers are growing. And it's good to see, because when I am like, I opened this slide yesterday and checked the tools, and I saw that like, yeah, the numbers were growing significantly. So I kind of updated them, and that's good to know. So the question which I want to ask here is that, so many rules. We talk about the core guidelines, these DSL analyzers. There are many things. Are they really that different? So there is these rules in the core guidelines about the periodic functions. There are also these rules in MISRA about the same stuff if you read through them. And for example, there is also the same rule in the CERT guidelines. So actually, these things are quite often about the same. And that's interesting to notice, because my first impression was, while reading through all these different checks implemented in various tooling, was like, oh wow, I have to run so many tools on top of my code, but actually you don't. So many of them are just, about the same stuff. So there's maybe just different angles on viewing at it, but there are a lot about the same. When talking about the code analysis and the tools we have and the aspects, there are 3 more aspects which I would like to highlight, and they're very important. First of all is the formatter, because if we talk about the software quality, if we talk about the good code is the properly formatted code. And in C++, somehow I think that we nearly have the standard tool, that's the Clang format, but it has its issues, and you need to use it carefully and understand these issues. So from one perspective, yeah, it's kind of standard in C++ nowadays. Quite many, I guess, not maybe all, but quite many repositories, for example, on GitHub, if you open, you can find the Clang format config file inside. So you know how the community working on this code actually want it to be formatted. And that's good for you to apply this, config if you develop and if you contribute to this code base. The thing about the Clang format is that, yeah, it's kind of used to break compatibility between versions. That's not only in the terms that it has this fuzzy parsing, so it doesn't use it's called Clang format, but it's not using the fully functional Clang parser. So it has its own fuzzy parser, because that's how it achieves the better performance. So it's using the fuzzy parser, and it also evolves. So it could happen that, like, the way it parses from version to version, the way it formats the code is different because of that, because they also fixing things. They are fixing bugs, for example. But it also breaks compatibility in terms of the parameters, in terms of the configuration. So their parameters could be renamed, or, which I've seen quite often, is that when they change the set of the values. I mean, for example, there was a parameter which has true and false values, and then they change to some enum values. So the configuration you have is no longer valid, because the set of the values for this parameter has changed. So you need to think about it. You need to have it in your mind. So if you're using the tools which, for example, are bundling the Clang format, it might happen that you're using the different version. So you need to be accurate. So quite often the teams end up in using some specific version of the Clang format and relying only on it. So either all are using just specific version, or calling it on a pre-commit hook to make sure that everyone is on the same page. Okay, formatting, kind of simple if we have this specific in mind. Also, there are naming rules, and I truly believe that naming and proper naming is a part of the software with the good quality. It's part of the philosophy for the good quality software. So you have to name things properly, and you have to agree on the same guidelines inside the team. Otherwise, it's very hard to maintain this code base. There are different styles. I like how they name the styles, especially this screaming snake case. It's yeah, I don't like using it, but I like how it's called. Anyway, there are different ways, and sometimes there are different approaches how to do that, but the idea is that looking at the code and at the name of some entity in the code, you can quickly understand if it's a macro, or it's a function, or it's a member function, or it's a static function. We're using different naming guidelines for that, and they help us capture the idea behind the code quickly. And there are different code styles available. There are standard code styles. There are code styles which evolves from that. There are different tooling for that, and the tooling could not just, check and throw warnings into you, but it can also help. The complex aspect is that the challenging aspect is probably that the proper tooling which helps with the naming actually should do the proper rename refactoring, because if you want to fix the name, never do that by hand. I think Kate said that in the morning, and I will repeat it to you in the evening. Never do that by hand. I mean, call the proper rename refactoring. You might have the variable with the same name in the different scope and it is completely unrelated. Don't touch it. The rename refactoring will find that for you. Usually the proper rename refactoring is context aware, so it will rename properly. So the proper tooling just does the proper rename refactoring and usually integrates that naming rules into various like other refactorings or code generation abilities. So they also have to know about the naming rules. And yeah, naming, and also there are syntax style rules. And syntax style rules, that's exactly like, again, back to this example with returning 42. That's how we write the code. We can write C++ code in many ways that it's still correct, it's compilable, it does the job, but it looks different. And it's good to have one conversion. And that's what we're trying actually to do. There are lots of conversions. Sometimes they're controversial. Sometimes we're just, you know, East const and West const. Like we're all arguing about that. Also, I saw some controversial guidelines between, for example, LLVM code style and like Unreal Engine code style. We surprisingly noticed that they contradict in like many aspects here as well, but there are reasons for that, but still, so you have to know about that. So yeah, these syntax style rules, usually they're about like how to use auto, like where to place const, or what to use type defs or type aliases. So what about the like trailing return types, how to use override, all these things are like, in any case, the code will be correct, so you can write the proper code, but you could write it differently. And to avoid having like 10 ways of doing one thing in one code base, you need to follow the rules. We did the attempt to like make it toolable. To be honest, we spent like half a year maybe on implementing all these rules in C# C++. We had made a huge table with settings. I don't know if anyone configures it ever, but like it's possible. And it actually controls the thing, and that's quite natural for the IDEs because they have the AST, so they can control it easily, so it doesn't cost them anything. So they are anyway parsing your code, so they can do that, and they can implement these checks, and you can kind of force the syntax style rules you want to. Okay, so some small summary about the code analysis and how it goes in the modern C++. So first of all, we can just use compiler, and there is lots of help from it if you cook it properly. The language evolves, and it actually does its best to help us in many aspects which are painful, and for like help us to limit lots of frustration. There is a very powerful data flow analysis direction, and I hope that it will evolve and it will help us to capture more things. There is this fantastic effort with the core guidelines. Again, if we cook it properly, it could be for the good. DSL analyzers, which is a must if we're using some specific domain area, if we're working in some specific domain area. And yeah, the style is also important. But like, I want to ask you here, like, I was talking about lots of tools which helps us and about the tooling, but let's just check how often do we rely on tools for code analysis. We actually asked that in our like survey, in our developer ecosystem survey. Again, I have only the answers from 2020 and 2021. What do you use for guideline enforcement or other code quality and analysis? And the third of the developers using nothing, which is sad. And I really would like to limit this last part to the minimum so that we all are using at least something. You see that there is lots of tools from the Clang ecosystem here. So the people actually now understand that the Clang is doing some good job for them, not only as a compiler, but also as a whole ecosystem which helps with code analysis. And there are many, many people who just simply rely on what their IDE suggests, and luckily the IDEs evolve and they can suggest more. So I have some, small hope that we can limit this last part and make significantly less than 30% of the developers using nothing. Because, as you see, that's all for the good, so it actually has some benefit. And before I wrap up, I actually have to say that I haven't talked about many things here. Like, for example, I haven't talked about the code analysis on CI. I was mostly talking about the code analysis like while you're typing the code. There's a very powerful area of running the code analysis on CI. And I don't know how many of you were yesterday on the meetup, pre-conference meetup. Arnemers was talking about the code reviews. And he said that before doing a code review, you have to check that like the code in the branch actually compiles and all the tests are green. But I have to add, but you also have to check that the code analysis, the guidelines you agreed on inside the team on this code on CI are also all green. And after that, you can start with the code review. And that's what these tools are for. So I missed that part completely, but that's a whole new talk. So maybe I'll do that one day. So for now, just like a small sneak peek of the tools which are there in the community for us now. And yeah, some references if you're interested in some of the things I was talking here about. And that's it. Questions? No? Thank you.